Assalamu alaikum dear students. I'm your instructor Muhammad Ishaq for the course Electronic Design and Practice Spring 2020. This is lecture number 10. Today we will discuss the high frequency response of BJT amplifiers. So we have a amplifier, a BJT amplifier. This is a common emitter amplifier using an NPN transistor. Input is at base side and output is from collector side, and emitter is bypassed through capacitor CE. So this is emitter bypass capacitance. These are the source side capacitance. This is load side or collector capacitance. This is a NPN transistor and connected in common emitter configuration using a voltage divider bias circuit. So we would be interested in computing the frequency response of this amplifier. So this circuit have a response of kind of band pass response of this type. It has a low frequency response and a high frequency response and a mid frequency response. So at low frequencies the gain decreases as frequency is decreased from the lower cutoff. Similarly, the gain again starts decreasing as the frequency is increased above the higher cutoff frequency. So at these extremes the gain starts decreasing from its maximum mid-range value. So we have already covered the low frequency response in previous classes. The low frequency response is basically governed by the coupling and bypass capacitances, and high frequency response is dictated by these parasitic capacitances, which includes the junction capacitances and wiring capacitances. When we consider the high frequency response, then the response due to these capacitances would be calculated, and the other capacitances would be considered short circuited, because at high frequencies reactance of these capacitances that which are indicated in blue would become very low, and it approaches zero. So these capacitances would be treated as short circuited. However, in high frequency region these capacitances are no more open circuited, so they would retain in the circuit. In order to compute the high frequency analysis, we proceed in the way that this circuit is transformed into this form. This is basically the high frequency circuit model of this circuit. जो हम इस सर्किट से इस फॉर्म में या इस इक्विवेलेंट सर्किट में हम कैसे आए हैं, तो उसके लिए सबसे पहले हमने जो इस सर्किट में जो आपकी डीसी सोर्स है उसको आप ज़ीरो पे सेट करेंगे, ज़ीरो कर देंगे, और जो जितने भी आपके कैपेसिटर्स हैं, जो आपके कपलिंग और बाईपास कैपेसिटर्स हैं, उनको आप शॉर्ट सर्किट ट्रीट करेंगे, और जो ट्रांजिस्टर है उसको आप रिप्लेस करेंगे इसके इक्विवेलेंट आरई मॉडल के साथ। ये इसका आरई मॉडल है, जिसमें एक इसकी जो बेस एमिटर जंक्शन रेजिस्टेंस, जिसको हम डायनामिक रेजिस्टेंस कहते हैं, वो बीटा आरई है, और जो कलेक्टर और एमिटर के दरमियान जो इक्विवेलेंट रिप्रेजेंटेशन है करंट सोर्स के साथ, दैट इज़ बीटा आई बी। तो ये आपका आरई मॉडल है। ये आपकी जो कैपेसिटेंसेस हैं शॉर्ट सर्किट है, जो आपकी कपलिंग और बाईपास कैपेसिटेंसेस हैं वो आपने इनको शॉर्ट सर्किट से रिप्लेस कर दिया, और जिसकी वजह से जो आपका एमीटर है वो आपका ग्राउंड पे चला गया, और जो कैपिटल आर है वो इस कैपेसिटेंस को जब आपने शॉर्ट सर्किट से रिप्लेस किया तो ये बाईपास हो गया। सो जितने भी आपके कैपेसिटेंसेस हैं जो कि लो फ्रिक्वेंसी डिटरमिन कर रहे थे वो सारे के सारे शॉर्ट सर्किट हैं, और जितने भी कैपेसिटेंस हैं जो कि रेड में इंडिकेटेड हैं वो इस तरह से ही सर्किट में रिटर्न रहेंगे। सो देन हम इस सर्किट को हम फर्दर सिंप्लीफाई कर सकते हैं इनटू दिस फॉर्म. You can see that these three resistors they are in parallel. So इनको हम पैरेलल में सॉल्व करके एक रेजिस्टेंस में कन्वर्ट कर सकते हैं, which is R Thevenin I. So R Thevenin I is nothing but parallel combination of these three resistors, and R Thevenin naught is the parallel combination of these two resistors. So at the input side these three resistors form a equivalent resistance R Thevenin I, and at the output side these two resistors form an equivalent resistance R Thevenin naught. So R Thevenin naught would be equal to RC in parallel with RL, and R Thevenin I would be equal to R1 in parallel with R2 in parallel with beta RE. Then we can further simplify this as if we can see these two capacitors are in parallel. This capacitor is CWI and this capacitor is CBE. So these two are in parallel, so they can be just sum up to form an equivalent capacitance at the input side, and these two capacitors are also in parallel, so they can be added to form a single capacitance at the output side. So these two capacitances and these two capacitances are transformed into these ones. However, this capacitance which is between base and collector, this would just remain there in the circuit. So now this circuit is further simplified. So we are only left with these three capacitances out of these five capacitances. Further, this circuit can be simplified. As you can see, if we for the time being ignore this capacitance, then this circuit it has two portions. One is the input side and the other is our output side, and this capacitor couples these two input and output sides. So this is a capacitor which couples the input and the output. If we can decompose this capacitance or dissolve this capacitance, then this problem can be simplified, and we can isolate the input section from the output section. There is a theorem which is called Miller theorem, which help to simplify this problem. Miller theorem says that this capacitance which couples the input and the output can be decomposed into the two capacitances, one when you look the circuit from the input side and the other one when you look the circuit from the output side. So this capacitance have the equivalent reflected effect at the input and output ports. So as you can see, this circuit can be represented as a simplified block diagram as shown here. You can see this whole circuit is basically represented by this block which has two ports. One is the input port and the other is the output port, and this capacitance, this is a CF capacitance, which is also called the feedback capacitance, which couples the input and the output port, just like the scenario here, in which this capacitance, which is CBC, base to collector capacitance, which couples the base and collector. Base is the input and collector is the output port. So this theorem will help us to isolate the input and output sides. How? Let we proceed further. So this is the scenario. So in this scenario, when I look from the input port, then I will observe a reflection of this capacitance from the output port equivalently, where this input port is having input V in, and the current from this terminal is I in. So when I look from this port, the input impedance from this port is Z in, where Z in is equal to V in over I in. Similarly, when I look from this point, the resistance that offered is R in, where R in would be equal to V in voltage here divided by the current from into this terminal in this port. So अगर मैं यहाँ से ऑब्जर्व करता हूँ तो मुझे जो इम्पीडेंस नज़र आएगी वो Z in नज़र आएगी, और अगर मेरा पॉइंट ऑफ ऑब्जर्वेशन आगे शिफ्ट होता है और मैं यहाँ से देखता हूँ तो जो मुझे इम्पीडेंस नज़र आएगी या रेजिस्टेंस नज़र आएगी वो R in होगी। सो अभी मैं ये देखना चाह रहा हूँ कि जब मैं इस पोर्ट से देखूँगा तो इफ़ेक्टिवली इसका जो इम्पैक्ट होगा, जो कैपेसिटेंस CF है, उसका इम्पैक्ट मुझे इस पोर्ट से कितना नज़र आएगा। तो उसको कंप्यूट करने के लिए मैं सबसे पहले यहाँ पे इस नोड के ऊपर मैं KCL लिखता हूँ। तो यहाँ पे जो मैं करंट डिफाइन कर रहा हूँ, I in इस नोड में इंटर हो रहा है और I1 और I2 जो है वो इस नोड से लीव कर रहा है। सो KCL जो मैं जब यहाँ लिखूँगा तो KCL वुड बी current entering must be equal to current leaving, so I in would be equal to I1 plus I2. So I in would be equal to I1 plus I2, where I in would be equal to V in over Z in, and I1 would be equal to V in over Ri, and I2 would be equal to this. I2 would be equal to this current is flowing through the capacitance, so this current would be equal to voltage, this voltage minus this voltage divided by the impedance. So this voltage is V in here, this is V in at this point, and this voltage is V out at this point. So potential difference V in minus V out divided by the reactance would be equal to the current I2. So I2 is equal to V in minus V out over XCF. So this is V in minus V out can be written as AV into V in, because AV is equal to V out over V in, so V out is equal to AV into V in divided by XCF. So which is equal to V in can be taken out. So this becomes 1 minus AV into V in over XCF. So if I plug these values I in, I1 and I2 in this equation, so then resulting equation would be this one. So from numerator V in can be taken out and it would be cancelled from both sides, so I will get 1 over Z in is equal to 1 over Ri plus 1 over XCF divided by 1 minus AV. So इस फैक्टर को हमने इससे डिवाइड कर दिया नीचे यहाँ पे, तो दिस कम्स आउट टू बी दिस रिलेशनशिप. So let's focus on the denominator of this term, which is XCF over 1 minus AV. So this can be written as XCF is equal to reactance जो होती है वो होती है 1 over omega C होती है, तो मैं इसको लिख सकता हूँ 1 over omega CF into 1 minus AV. So अगर आप इस चीज़ को देखते हैं ओमेगा के साथ जो ये फैक्टर मल्टीप्लाई हो रहा है, तो इसको मैं लिख सकता हूँ CM, चूँकि ओमेगा के साथ जो फैक्टर मल्टीप्लाई होता है वो होती है कैपेसिटेंस. सो ये जो ओमेगा के साथ इंडिकेटेड जो टर्म है तो वो सारे के सारे उसको मैं कह सकता हूँ C, and M is for Miller. So this is called Miller capacitance. So 1 over omega C जो होती है that is equal to XC. So this would be equal to 1 over omega CM would be equal to XCM. So this is called Miller capacitance, Miller capacitive reactance, and this is called Miller capacitance. So 1 over ZI would be equal to 1 over RI plus 1 over this whole thing, which is equal to XCM, this XCM. So from this equation you can see that RI and XCM are in parallel, because 1 over R equivalent is equal to 1 over R1 plus 1 over R2. That this relationships show that R1 and R2 are in parallel, or you can say Z equivalent would be equal to R1 in parallel with R2. So this capacitance would be equal to which basically appears here here in the parallel with this. This would be cancelled. This is the effect of this is the effect of this capacitance when you look from this port, and this is in parallel with this Ri. This is where this is Ri. This is Ri. These two are in parallel like this. So these two are in parallel. So with the application of Miller theorem, any capacitance which couples the input and output port that has a reflected effect on the input port, and that is computed using Miller theorem, and it would appear as a capacitance CMI, Miller input capacitance. This capacitance is the reflected effect of this capacitance, and its value is equal to CMI, is 1 minus AV into CCE, where CCE is the this is CBC. CBC, which is collector capacitance between base and collector terminals. This capacitance is the effective capacitance, Miller input capacitance, and if you go back at this slide, you can see if this capacitance have effectively a capacitance reflected effect at this port, then this capacitance would be effectively appears at this port, in parallel with this capacitance. Like this. So these two capacitances become parallel. So effectively they can be added like CI in total input capacitance at the input side of the two-port equivalent circuit would be CMI Miller input capacitance plus CWI plus CBE. So this is the total equivalent capacitance of the input side, and this is the input side. Similarly, we can see the effect of Miller output capacitance, which is the reflected effect of this capacitance when we look from the output port and proceed with the same way. And if I indicate a node at this output port, then the case I can apply KCL and proceed with the derivation. I will arrive at this conclusion, which is indicating the Miller output capacitance, and this Miller output capacitance will appear at the output port here, reflected effect of this capacitance, and this becomes in parallel with the other capacitance as shown here. So effect of this from the output port would be a capacitance which is Cm naught and is in parallel with this capacitance. This capacitance is a parallel combination of these two. So effectively these two also becomes parallel like here. So as a result, the total output capacitance would be equal to Cm naught plus CCE plus CW naught, CCE and CW naught. So this is the Miller output capacitance, that is equal to 1 minus AV into CF. CF is the feedback capacitance, AV is the gain of the amplifier, V out over V in. So please note that this gain is negative because our amplifier is the common emitter amplifier, and common emitter amplifier has a negative gain. So when you plug minus here, this minus and this minus becomes plus, so the capacitance would always be a positive number. So for a usual situation where gain is very greater than 1, so if gain is very greater than 1, then 1 over gain would be approximately equal to 0. So Cm naught would be approximately equal to Cf, which is the feedback capacitance. This is only true for if gain is very greater than 1. So total input capacitance is sum of these capacitances, and total output capacitance would be sum of these capacitances, which results in the total input capacitance Ci at the input side and C naught at the output side. I can join these two ports because both are at the ground terminal, so potential would remain 0 at this link. So effectively all those capacitances which are wiring capacitances, junction capacitances, and now the Miller capacitance, which is the capacitance that couples the two ports and are decomposed into these capacitances, they are all added to form one capacitance at the input side and the other capacitance at the output side, which is C naught, which is the output wiring capacitance, junction capacitance, and the Miller output capacitance. So you end up with the simplified circuit which now contains only two capacitances out of many, and a series resistance for each capacitance. With this series resistance is the Thevenin equivalent that is computed when you look from the capacitor side. So when you look from the capacitor side towards the left, these two resistors becomes parallel, as when you Thévenize this circuit from this port, then input voltage source has to be put to ground 0. So when you put this point at ground 0, then these two resistors become parallel, and total Thevenin resistance would be equal to Rs in parallel with R Thevenin I, where R Thevenin I is the parallel combination of R1 and R2 and beta Ra. So Rs in parallel with R1, R2 and beta Ra. Similarly, at the output side, you can see that here we have a current source and a resistance. This current source can be converted into voltage source, so result would be a voltage source in series with this resistance. So this resistance was basically a parallel combination of RC, RL and R0. So this is RC, RL and R0. So you end up with this simplified circuit in which you can see both have the same topology, resistor and a capacitor, a resistor and a capacitor. So this individual section form a simple first order filter, and this filter would be a low pass filter. You have already seen a high pass filter in which capacitor is here and resistor is here, but this is the opposite case. Resistor is sitting here and capacitor is sitting here, so this would be a low pass filter. This would also be a low pass filter. So a low pass filter has this kind of topology: resistor and a capacitor. Capacitor sits in parallel with the output. So when you derive a transfer function of this circuit, or gain of the circuit, then you end up with this relationship in which you can see this vector has the variable frequency, so gain would be function of frequency. This is a complex expression. It has a magnitude and has a phase. So magnitude response, if you plot it with frequency, it would show this kind of response, which is at low frequency gain would be maximum, but as you increase the frequency, gain would decrease, and at a certain frequency, which is defined as the cutoff frequency fH, the gain would be at minus 3 dB. So this is the cutoff frequency, which where the gain would be 0.707 of the maximum value, or minus 3 dB point. So this cutoff frequency is fH, and is can be determined from the component values using these parameters. So fH of the circuit would be equal to 1/2 pi R into C. So you can derive this relationship, and you can prove this relationship as we have done with the low pass filter. In previous classes we have derived that relationship with the high pass filter. So same can be done with this circuit. So you have one low pass filter and the second low pass filter, so you will get two cutoff frequencies, one for this and one for this section. So for the input section, the cutoff frequency would be equal to fHi, and it would be equal to 1/2 pi R into C. R is R Thevenin I and C is the Ci. So 1/2 pi R Thevenin I into Ci. So where R Thevenin is this and Ci is this. Similarly, for the output side, the second cutoff frequency that would be equal to 1 over 2 pi R into C. R is R Thevenin and C is C naught. So R FH naught would be equal to 1 over 2 pi R Thevenin naught into C naught, where R Thevenin naught is this parallel combination and C naught is the sum of these capacitances, and this is C naught. So for the given parameters you can find FHI and FH naught if you are given with these component values and these capacitances. This capacitance can be computed using this relationship, and these capacitances you can compute these two frequencies from these relationships FHI and FH naught. These two frequencies basically each define a minus 6 dB per octave asymptote, such as depicted in figure 9.46. So this is figure 9.46. This is the asymptote which indicates a roll off of minus 6 dB per octave above cutoff. So these two cutoffs would be indicated as FHI and maybe here FH naught. So another roll off you will get at this point, depending upon which frequency is higher. If FH naught is higher than FHI, then it would lie ahead of FHI.